Hello everyone, I'm Joseph and I'm going to take us through a question in the past paper of Fluid Mechanics Advanced. This was the paper for 2019 and I'll go through question number 2. Part A, with the help of a well-labeled illustration, explain the basic components of a hydraulic system. So a hydraulic system is comprised of the following components. It has a reservoir, it has the pipes, it has a pressure regulator, it has the actuator, it has the directional control valve, and it also has a filter and a pump. So all we have to do is to organize these parts and make them into a piping system that is going to make the hydraulic system. Start from the reservoir. So we start from the reservoir. The fluid from the reservoir goes through the system by the energy provided by the pump. So this is the pump, and the pump is driven by a motor through this coupling. This is a filter so that our pump is not blocked or spoiled, so we have a filter. This is a breather. In case the pressure inside here is too much, it can always breathe. So this is a breather. This is a pressure regulator so that the components of the system are not affected. The pressure regulator helps. Then this is the directional control valve. It controls the direction of the flow line. When the fluid moves out like this and it reaches the directional control valve, the control valve either makes it flow downwards so that it pushes this load inwards, or it makes it flow through this other pipe system so that it pushes the load outwards. And this is the actuator. In this case, it is a cylinder. Basically, that is the system. So we've been asked to, with the help of a well-labeled illustration, explain the basic components of a hydraulic system. So this is the illustration, and the components, I listed them earlier and I've talked about their importance. The reservoir keeps the fluid. Pump provides energy for the fluid to flow. Pressure regulator regulates the pressure so that there's no excess pressure in the system to damage it. The filter filters the fluid free of any foreign material so that our pump is not damaged. The motor drives the pump. The directional control valve controls the direction of flow of the fluid. The cylinder actuates the hydraulic energy. Basically, that is it. So we can look at part B. An automobile lift raises a 15,600 Newton car 2.13 meters above the ground floor. If the hydraulic cylinder contains a piston of diameter 20.32 centimeters and the rod of diameter 10.1 0.16 centimeters. Determine 1. They want us to determine work done, pressure required, the power, descending speed, the flow rate. So to make most of these calculations in the engineering perspective easy, it is always better you draw some sketch. So we have a fluid coming in from down. When it enters this lift, it pushes the piston up. This is the piston, and this is the rod. So when it pushes it up, it raises this load from maybe point A to point B. The load has now moved to some other new point. And the distance traveled is 2.13 meters. The load, we've been told, is of 15,000, so it is of 15,600 newtons. And we've been given the diameters. So the first part requires us to find the work done. Work done is equal to force times the distance. Of course, the distance traveled in the direction of the force. So the force is the weight of the load itself, the car. The car is of this weight, so the force applied down here is to lift the load, meaning this force is just counterbalancing that. So we shall take the force as 15,600 times the distance of travel is 2.13. So we get 33,228 joules. That's part 1. Part 2 asks for the pressure required. Pressure is equal to force out of normal area. The force is still the load or the weight of the car. Now the area to use is all that we have to sort out. When the load is applied on top here, that weight is in contact with the fluid through this base of the piston. So the area we shall use is the area of the piston. And area is pi out of 4 d squared. So that becomes pi out of 4, and d is, we were given d as 20.32, so 0.2032 squared, which gives us, so that is the area, and pressure becomes 15,600 out of 0.032. So the pressure required becomes, and this can be written as 481.05 kilopascals. That is part 2. Part 3 is the power if the lift raises the car in 10 seconds. Power, this is part 3. Power is equal to work done out of time. The work done was 33,228 joules out of 10. So that becomes 3,322.8 watts, which can be written as 3.32 kilowatts. Roman 4, the descending speed of the lift for this flow rate given. Roman 3 has given us a flow rate of 0.000629 cubic meters per second. Now, if you want to lower this load from B to A, you just have to open this valve. You just have to open this valve so that the fluid flows out under the pressure due to the load. So as the fluid flows out at a certain discharge, the load will be descending down. So as it descends, it means we are going to use the equation of continuity, that Q is area times velocity. The area we shall use is the area of the piston because the load is in contact with the fluid with that area. So we need velocity becomes the flow rate out of the area. We got the area there as 0.032. So we get velocity as 0.0197 meters per second. And we have part 5, the last part, flow rate for the automobile to descend in 10 seconds. Now, we are being asked that if this automobile is going to move from B to A in 10 seconds, how fast should the fluid be discharged from the cylinder? Still from the equation of continuity, discharge is area times velocity. The area is known. All we need to know is the velocity with which this body has to descend, this car has to descend, so that we can know the discharge. Velocity will be given as distance out of time, the displacement, and since it was raised through 2.13 meters, if it is to descend to an initial position, it should go through 2.13 meters. So that is 2.13 out of 10, giving us 0.213 meters per second. Therefore, the discharge shall be area times the velocity. And that gives us 0.0068 cubic meters per second. Thank you. That's all I had.